Namaskar and welcome back to another lecture in this course on Infrastructure Asset Management, which is being offered under the MOOCs initiative of the Government of India. And a statutory kind of warning that the material used in this course is strictly for academic and instructional use in this course, and it is not expected that it will be used for any other purpose. What you see on the screen is like the blackboard in the good old days. Please make it a habit to make notes as usual, using what is projected and what is stated as a input. Moving forward, this week we will talk about maintenance of concrete structures. Today we will talk about carbonation in reinforced concrete structures. To recapitulate what we have done so far in this course, we started with an overview of the course content, including the conduct and of infrastructure asset management as such. We moved on to talk about a schematic representation of the deterioration and performance versus time graphs and an examination of the concept of service life and maintenance action in that framework. We talked about case studies which highlighted the role of different stakeholders in different phases of the project and the importance of a comprehensive strategy towards infrastructure asset management. We talked about decision making frameworks, including performance modeling considerations in budget allocation. Moving forward, what we will do today is to initiate a discussion on the specific technical issues involved in infrastructure asset management with simple examples. For example, we will discuss in some detail issues relating to carbonation in reinforced concrete structures in light of the general framework that we have already discussed as far as infrastructure asset management is concerned. We will try to avoid an overdose of technical details, keeping in mind the promise that this course is primarily for management of infrastructure and technical details are included only to facilitate better understanding of technical issues by non-technical asset managers. We have already talked about deterioration in concrete structures as an important part of the asset management or asset maintenance procedures. Some time ago, possibly in module 1, we had talked that over the years the following have been identified as major mechanisms that cause deterioration in concrete structures depending on the environment in which the concrete structure is. For example, we had talked about chloride induced reinforcement corrosion, carbonation induced reinforcement corrosion, alkali aggregate reaction, cyclic exposure to freezing and thawing, chemical attack and so on, and we had seen photographs or images of deteriorated structures on account of long exposures to these environments. Today, we will concentrate on carbonation induced reinforcement corrosion and the considerations that go there from the point of view of IAM. Now, what is the process involved in carbonation? If we look at a concrete structure which is schematically represented here, we have a reinforcing bar which is protected against the environment using this covered thickness which is of obviously concrete. And this here is the main body concrete. Carbonation as a process refers to the penetration of carbon dioxide from the atmosphere into the pores of concrete. What this really shows is that concrete is a porous material, except that the porosity is not such that there will be a sponge-like action, but yes, nonetheless, carbon dioxide from the atmosphere can permeate through the concrete as is shown here. Now, this ingress leads to its reaction with calcium hydroxide within the pores, leading to the formation of calcium carbonates and bicarbonates, and that is what is represented through this reaction here. Calcium hydroxide and carbon dioxide gives you calcium carbonate and water. Now, where did this calcium hydroxide come from within the pore structure? This is an important product of the hydration of cement. when cement hydrates, large amounts of calcium hydroxides are formed. This calcium hydroxide is sitting in those pores, and when carbon dioxide comes in, it reacts with this calcium hydroxide to give you calcium carbonates and water. So, basically the carbonation process leads to a consumption of calcium hydroxide and a consequent reduction in the pH. So, the pH of the pore solution of a cement concrete is often reported to be in excess of 12, and that reduces once the calcium hydroxide present therein is consumed on account of carbonation. Also, the process leads to the deposition of calcium carbonates in the pores. Now, this in a nutshell is the process involved. Now, if we look at it diagrammatically, this is what happens. So, initially there is a lot of calcium hydroxide available throughout the cover concrete. So, this basically is my cover concrete, and on account of hydration, a lot of calcium hydroxide is present in a uniform concentration throughout the depth. So, this in a manner of speaking can be taken as concentration. So, we are talking of a uniform concentration of calcium hydroxide to begin with. Now, as carbon dioxide permeates into the concrete, what happens is that the calcium hydroxide present in this zone, which let us say call is zone 1. In zone 1, this carbon dioxide and calcium hydroxide, following the reaction that we saw last time in the last slide, we have something like this, which means calcium hydroxide is getting consumed and calcium carbonate is being formed. So, basically what is happening is that calcium carbonate is being formed in this zone. In this zone, we still are at close to the initial concentrations of calcium hydroxide, and this zone 2 is some kind of a transition in between. That is, this has a mix of calcium hydroxide and calcium carbonate. Here we have primarily calcium hydroxide still, and here we have calcium carbonate, and in a very extreme sense we can say that we have lost a lot of calcium hydroxide. As a result of this change in the calcium hydroxide concentration across the depth of the cover concrete, this zone has a pH which could be less than 9. This zone is still having a pH of greater than 12, as I mentioned before, which is the pH of the original hydrates or the pore solution with the original hydrates, and this is a transition zone where the pH could be anywhere between 9 and 12. Now, with this basic understanding, let us move forward as to how this thing is measured. The measurement of carbonation thickness is done by spraying phenolphthalein solution. If we look at this kind of a picture here, we find that the colorless portion is used to estimate the depth of carbonation. We can see here, and then estimate the thickness or the place where the carbonation front is. That is, till what place or till what depth from the surface, because the way it is shown here in this diagram, here is the surface of concrete which is exposed to a certain concentration of carbon dioxide. So, the way this picture is shown, possibly carbon dioxide is permeating through all the 4 faces, and we find that there is colorless portion here, there is colorless portion here, there is colorless portion here and here. Note that these depths are very difficult to quantitatively measure, and that is something which we will talk about later on in this discussion. But yes, this is what the phenomenon is. That is, this colorless portion reflects those areas where we have lost a lot of calcium hydroxide which should have been originally present, and the pH has been reduced. This picture here shows carbonation in cracked concrete. In fact, if there is a crack in concrete the way it is shown here, carbon dioxide does not penetrate only from the surface, but also through the crack and then permeates inside through the crack, which means that the carbonation front moves not only like this from the surface, but also in a zone which is around the crack. And this depth obviously is very close to the depth of the crack itself. So, moving forward, if we put these two pictures together, this picture we have already discussed in great detail. This picture has now been simplified into a picture like this, which says that okay, here is the uncarbonated portion, which may have a very different kind of a shape. It is not necessarily a straight line the way I have shown it, and this depth here is carbonation depth. That is, this is the depth which has been compromised, if you want to use that word, and the environment here is basically from where the carbon dioxide is going into my cover concrete, which is there to protect this steel. So, this carbonation depth as a function of time will increase. What would be the carbonation depth at t is equal to 0? This depth, if we call it x, this x at t is equal to 0 will be 0. As this time keeps increasing, this depth will also increase. Now, the rate at which it increases will depend on what is the rate at which the carbon dioxide is penetrating into this concrete. If the concrete is such that the penetration is difficult, the porosity is low, then the carbonation depth will be small for a given time. If the porosity is high, then the carbonation depth for the same time would be higher. With this understanding, let us formally look at some of the basic issues in carbonation. Concrete is a porous material that allows passage of material, although at a very slow rate. The porosity of concrete is related to parameters such as the water cement ratio and the quantity and properties of cement used in the concrete. So, if we have in a concrete a greater amount of cement, so the amount of cement is high, then we can expect the porosity to be low. When the amount of cement is high, typically we would associate water cement ratio to be low. Also, in the present situation or in the present scenario, when the cement could be pozzolanic, that is, it could have fly ash, it could have silica, it could have slag. In the present day situation, where the cement need not be the pure OPC, but it could have varying degrees of fly ash or slag or silica fume in it, then the amount of this calcium hydroxide available could be different for different cements, and therefore, for the same amount of cement, we could have different amounts of calcium hydroxide sitting in the system. Now, if the amount of calcium hydroxide sitting in the system is different, then the rate of progress of the carbonation front will also be different, because if the calcium hydroxide is low, for a certain amount of diffusion that takes place, the depth of penetration will be higher. So, these are some of the things that we must keep in mind. These are technical details and are easily understood, I suppose, by even people who are not necessarily trained in concrete engineering or concrete construction. Care needs to be taken during and immediately after casting in terms of compaction and curing, etc. Because the concrete, during casting, we have to be careful about compaction, and after casting, we need to be careful about curing. Because if these two things are not done properly, the concrete in our structures will not be of the best quality or the quality which it has the potential of being. So, for the same concrete which has been mixed, if it is not compacted properly, will have voids, and those voids make it much easier for the carbon dioxide to penetrate into the system. Similarly, if the curing is incomplete or enough attention is not given, to this process, the hydration is not complete. And if the hydration is not complete, the extent or the amount of calcium hydroxide available in the system is reduced. So, these are some of the things that are important to understand, that it is not enough to simply say that we should use a concrete which has a water cement ratio of so much or the cement content of so much. It is equally important to ensure proper workmanship, which ensures proper quality in the concrete construction, and these have long term implications. Once the concrete is cast, set, cured and the structure goes into service, there is absolutely nothing that can be done to restore quality. We have to just live with that quality, and that is why during inspection some of these things come out, and that is what we are going to talk about again at a later point in the lecture today, and we have alluded to this in our earlier discussion as well. Moving forward, what are the implications of carbonation? First of all, changes in properties of concrete on account of the consumption of calcium hydroxide in the system and deposition of calcium carbonates in the system. The second thing is resulting reduction in the pH of the pore solution, which beyond a threshold means that the reinforcing bars are no longer in the protected range of pH. We have to remember that the reinforcement is rendered vulnerable to corrosion, which if it happens could result in cracks and spalling of concrete and reduction in the area of steel provided. Now, before moving forward, a brief view on how or why the reinforcement in the concrete corrodes. This picture here shows a reinforcing bar and a passivating film which is stable in the environment of high pH only, and that is why if the pH goes down, this passivating film is no longer stable. So, what is written here is, in the high pH environment, a dense film of gamma iron oxide which acts as a passivating film is formed on the surface. What we are talking about is that this film here, or the presence of this film on the reinforcing bars, protects the bar from directly coming in contact with oxygen or water which is present in the concrete, and this interaction, if permitted, is precisely what corrosion is. So long as this film is intact, the iron surface or the steel surface is not open to reaction with water and oxygen, as I explained to you just now. Having said that, if the cover concrete is carbonated, then the pH is lowered, as I already showed you, and even though the passivating film could be stable on one side, it could be destabilized on the other side because of the reduced pH. Now, if that happens, the passivating film being lost, the surface of steel becomes vulnerable to corrosion, and once corrosion happens, we have a situation like this, that is spalling of concrete, that is the cover concrete here, here and possibly here. We see that the cover concrete has fallen off, and also the steel has corroded, which means that the area of cross section that we had provided for might have reduced by a certain amount. That how much is the amount will depend on the extent of corrosion. So, in order to avoid a situation like this, we need to be careful and plan as to how much carbonation can be permissible in the service life of the structure. That is the framework that we had talked about in module 1, and we are going to talk about it more in detail today. Now, let us look at the analysis and design perspective that we talked about in module 1. Recall the discussion on analysis versus design. What we had said was that analysis basically means that given the system characteristics and given the input, what is the output, and in design, for a permissible or acceptable output, given that input, what should the system characteristics be? That was the basic difference, and now putting carbonation in that perspective, what we find is that what will be the carbonation depth at the end of the service life given the concentration of the gas in the atmosphere and the material properties of concrete, which govern the porosity of the matrix and exposure conditions. For example, things like internal columns of a structure versus external columns of a structure are protected to different extents when it comes to rainwater, and that presence of rainwater means the external columns are likely to go through some kind of wetting, which will prevent the ingress of carbon dioxide into the concrete, whereas internal columns are typically not wetted in the service lives. So, these are some of the conditions which would impact the rate at which carbon dioxide permeates into the system. So, given the concentration of the gas in the atmosphere, material properties and environmental conditions, what would be the carbonation depth at the end of service life? That would be the question that is asked from an analysis perspective. Moving towards the design side, the question would really be, what should be the cover and the concrete properties such that the carbonation depth at the end of service life does not exceed a certain value, given the concentration of the gas in the atmosphere and other microenvironmental conditions. I hope this statement and the statement that we saw on the previous slide brings out clearly what we see from the analysis and design perspective as applied to the situation or the scenario of carbonation in concrete structures. Now, coming to the management side. In the case of carbonation, we could use the measurement of the carbonation depth at different points in time as a part of the normal inspection procedure. That is, we measure the carbonation depth at time t is equal to T1, T2, T3, and this depth that we measure would increase. Obviously, as the time increases, more and more carbon dioxide will go in, and this carbonation depth from here to here to here to here, it will keep on increasing. We should be prepared for this increase. And what we are doing during this inspection procedure is only trying to find out whether our estimates which were made at the time of design are accurate, inaccurate, safe, unsafe, and so on and so forth. This could be used to help make mid-course corrections in case when the estimated and actual values of carbonation are different, and obtain more realistic estimates for the rates of carbonation. We are going to reiterate this several times as we go along in these slides. Moving forward, we can compare the actual progress of carbonation front with the estimated values and take appropriate action. Note that measuring carbonation from structures is not a non-invasive test, and therefore only limited values can be taken. See, for example, if we were to measure the carbonation in this particular structure, what we will have to do is to take some kind of course from somewhere in the structure and try to find out how much is the carbonation depth here, how much is the carbonation depth here, and how much is the carbonation depth here. So, this taking of cores or taking out samples from the concrete is not really a non-invasive procedure, which means that we have to tamper with the structure. The owners of structures often do not allow that. Moving on, there could also be a reasonable amount of variation in the values recorded given the nature of concrete. See, concrete by the very nature is not a homogeneous material. It is homogeneous in a very large sense of the word at a macro level, but in a micro sense, the properties of concrete here and the properties of concrete here and the properties of concrete here could be quite different in terms of whether you hit an aggregate there or the aggregate is at a lower depth and so on and so forth, which means that the depth of carbonation that you measure, that is the carbonation depth CD, could be different at any point in time if you measure it here versus if you measure it here. And that poses a challenge to the managers as to how to handle the variations that you record. We may record 5 values at some time, another 5 values later. Should we take the average? Should we take the maximum? Those are things which need to be hammered out and laid down as a part of the SOP. There is always a possibility that instead of working with the actual structure in the planning, design and construction stage, we designate testing blocks in non-critical areas of the structure for this purpose. That is, we have a structure and we have designated testing blocks which could be used to study the changes in the properties of concrete. And in that sense, surely the depth of carbonation is just a property of the concrete at that point in time. So, if we are able to measure it using these designated testing blocks, nobody will have an objection, because those testing blocks are not integral to the actual structure, and taking out some concrete, doing some cores, taking samples and so on does not affect the structural integrity of the actual structure. But that is an action which has to be taken at the planning, design and construction stage. And that is why we are emphasizing throughout this course that effective infrastructure asset management begins at the planning stage itself. Moving forward. So, let us take an illustrative example. Based on literature, the growth in carbonation depth, which is designated as CD here, has been represented as CD is equal to K times root of T, where T is the time and K represents the properties of the environment, concrete and so on and so forth. So, what is being basically said is that if we have environment here, the progress of the carbonation front, which is being represented here, which is the carbonation front, with time can be represented as, if this depth was x, then this x is equal to K times root of T, where K is the constant here and T is the time. Please note that this equation is not dimensionally consistent, and therefore, the constant K is not dimensionless. Also, it is of interest to mention that this equation is largely based on empirical evidence, that is, through the study of a lot of field data and experimental data collected over different concretes in different environments at different times. So, with all that information collected, it was found that one simple way of representing the progress of the carbonation front with time would be to represent it in a root T kind of a model. This in fact is sometimes also referred to as the Kishitani model, and I would submit or request you, especially those who have a technical background and have an understanding of concrete, would like to understand concrete better, to consult specialized literature and understand this equation and its limitations a little bit more. Moving on, let us compare the cover requirement for two cases. One, when we want the structure to have a life of, let us say, 49 years, and another if we want the structure to have a life of 100 years. So, basically what we want is the depth of carbonation should not exceed the provided cover at 49 years or 100 years, whatever we want. Now, how do we go about doing this? So, if we knew the K, that is the permeability of concrete, and we have designed our water cement ratio and so on to get a certain K, then what is the cover requirement? The cover requirement in the case of 49 years, let us say what we are calling is L, L for 49 years should be greater than K times root of 49, which is 7 times K, whereas the cover in the case of 100 years should be greater than K times root of 100, which is 10 times K. So, what we are seeing is that if we double the life from 49 years to 100 years, the depth requirement from the point of view of carbonation is increasing by about 50%, from 7K to 10K. So, it is about a 50% increase, and that actually tells us as to how the progressive carbonation happens. I am leaving it to you to think, if we were to try to determine the rate of carbonation from this equation, how would we go about doing it? We would just try to take the derivative of this C d with respect to time, and I am leaving it to you to carry out that exercise and see for yourself how does that rate depend on the instantaneous depth of carbonation. So, that is an assignment left to you. Moving on, what I just stated is what is given here in the text, that the above equation gives the required cover depth as 7 K and 10 K. In other words, if we double the life, the required cover thickness for the same concrete, and this is what is the idea of same K, the required cover thickness for the same concrete is to be increased or needs to be increased by about 50%. If we do not want to do that, there is an option of trying to use less permeable concrete. So, if we would like to use the same cover as let us say 7 K, the K required for the case of 100 years should be lower than the K that we had in the case of 49 years. So, basically what we are playing with is the length of the cover, which is L, and the properties of the concrete, which is K. Now, this is exactly what we have discussed in a previous slide also, where we want to do the management of carbonation induced damage in concrete structures. As we have talked about a couple of slides earlier, when we do a mid course evaluation, what we are really trying to do is to find out the depth of carbonation at time t1. We already know what the expected value of this x at t1 should be, given the fact that we had an estimate for the permeability or the K value. Now, if at that t1 the actual value is greater than this expected value, let us say alpha, if it is greater than this alpha, then the deterioration is progressing at a rate higher than expected. Obviously, if the actual value is less than alpha, then the actual depth of deterioration is lower, which means that we somehow have a concrete which is performing better. So, in a nutshell, the life of an asset manager who is concerned about carbonation induced deterioration in concrete boils down to comparing the actual values of the depth of carbonation, which can be taken as the level of deterioration, and the estimated values, and taking appropriate action. So, that is what we are going to do in the next few slides and show you by examples, and that is what we can call some kind of a durability based design for carbonation in RC structures. So, what we do is, after carrying out the structural design in the normal manner, an additional check be carried out to ensure that the durability is there by checking something which could be similar to cover provided, the C shall be such that it exceeds the expected depth of carbonation D at the end of service life of the structure by x mm. What is being said here is that here is my reinforcing bar. That means, I have this cover C, which I have taken from a structural design kind of considerations, which is the traditional design. What we should check is that the concrete that we have used, we get the K involved, we already know the service life, let us say T, and for this T and this K we can calculate CD, that is the expected carbonation depth. Now, if we want to protect this reinforcing bar, we need to ensure that the C is greater than CD in the first place. That is, the cover provided should be greater than the compromised carbonation depth at the end of service life. What is being said here is a further factor of x. That is, if we look at this picture for example, and say that this is the carbonation depth that we get at the end of the service life, then how far are we from the reinforcement? This distance. This is what is the expected depth of carbonation at the end of service life. This is the cover provided, and this cover, the way it is shown here, is exceeding this CD by this amount x, which means that we have this as a reserve which is available to us at the end of service life, and the reinforcement is appropriately protected. Of course, we need to know the rate at which the carbonation front moves into the concrete, and for that we should know the relevant properties of concrete and its constituents, water cement ratio, the type and amount of cement, the conditions of exposure, and so on and so forth. And of course, the X can be fixed considering the importance of the structure. If the structure was something which is very important, and that is what we had alluded to when we had talked of the concept of consequence of failure. The structure is such that the consequence of failure is high, then this X, the reserve depth that we have, should also be high. Whereas, if a structure is such that the consequence of failure is low, then we can probably live with a lower reserve carbonation depth. All this discussion has the underlying assumption: if carbonation front reaches the location of the reinforcement, the latter is rendered susceptible to corrosion, and the reinforcement cannot be rendered susceptible to corrosion during the service life of the structure. So, with these underlying assumptions, we have tried to do the carbonation based durability design and also illustrated to you how the issue can be handled during the management phase. With this, we come to an end of the discussion today, and like always, I will share with you a list of references or material for further reading, which will help you understand the subject matter covered today and being covered in this entire course. As always, I express my thanks to my teachers, colleagues and students over the last several decades who have contributed directly and indirectly to my understanding of infrastructure creation and maintenance. Thank you, and I look forward to seeing you in another class later on.